Any time of no work. And let me laugh for full day.
Wow.
Guys, you know, when taxis have been done. They got indoors.
Ini ke?
Ah, look, I was.
Ele.
You know, no work. I want the new pump to take a bit. I want to. So, you know, Marcel to am. I want team of Marcel to am.
Can we mute our, please, this is online class. If you come online, the noise, please, you are disturbing the whole class, and it's recommended that if you are attending an online class, you go to a place where there is no noise, please. Okay, so let's continue from where we stopped. So we were looking at this function, and so it was example thing 3. So we have a function like h of x, that was 2x plus 1, I assume, yeah, over x raised to the power of 2 plus 5x plus 6. So we have this. So first off, I always tell you if it's a fraction, just take the denominator and equate it to 0. So I also explain it why we are doing that, because we want to find the value of the x where denominator is equals to 0. So I will use factorization. You can use general quadratic to also solve this. So what it means, I will focus on these two things when it comes to factorization. Obviously, this also is important. But first of all, find two variables. If you multiply them, it will give you x squared. Obviously, the candidates are x times x, because x times x will give you x raised to the power of 2. So we also look for two numbers. When we multiply them, it will give us plus 6. Obviously, it can be 6 times 1, that will give us 6. It can also be what? 3 times 2, that will give us, this is 3, by the way, is 6. So which one should we take? So to decide, first 6 plus 1, it will give us 7. 3 plus 2, that will give us 5. So that 5, if you add them also, those two factors, if you add them, should be able to give you the number here. That is the linear component, the coefficient of the linear component of the quadratic equation. So we can't use this, but we can use this. And how do we decide? That is, if two factors, if you add them also, should give you this. Should give you plus 5. So 3 and 2 is the best candidate. They are plus. This is plus, obviously, if it's not indicate, if there is no sign there, and this is plus as well. So at the end of the day, if we times this will give us what? Plus 6. And if we add them, it will give us what? Plus 5. So this plus 5. So these are our two. Now we have factored this. We have factored this. So what this is telling you, that is x plus 3 in another bracket, x plus 2 equals to 0. So if we expand this, remember, it should give us what? X raised to the power of 2 plus 5x plus 6 equals to 0. So then we have this, it will be x plus 3 equals to 0, or x plus 2 equals to 0. So obviously here x will be what? Minus 3, or x equals to minus 2. So what are these numbers? these numbers, they will make this denominator to be equals to 0. So we have to exclude them from the domain. So if you substitute -3 here, it will make this 0. If you substitute x equals, if you substitute -2 here, this formula, that is denominator, it will make the denominator 0. And division by 0 is not allowed. So we have to exclude this -3 and -2 from the domain of function h. So at the end of the day, the domain of function h will be equals to what? All real numbers. By now we know what are real numbers. Minus what? -3 and -2. So this is the answer. So what this mathematical notation is telling you that the domain of this function h, is all the real numbers. And we know the real numbers are what? Is plus, between plus infinity and this. But within this, we have -3 and -2. So, but we have to exclude this from the domain. We have to exclude them. Because why are we excluding them from the domain? Because if we substitute in the function, it will make this denominator 0. If we substitute -2 here, it will make this one equals to 0, or -3, it will make this equals to 0. So because of that, then we have to, exclude them from the domain of a function. So in some textbook also, they can equally write it like this. The domain of function h is what? Is all set, where x takes all the values of real number such that x is not equals to -3 and x is not equals to -2. So whether you use this notation or this notation is the same thing. It depends on you. So that's it. So that's our final answer. The domain of this function h is all real numbers except -3 and -2. That's the English interpretation of these two notations. So let's look at an example whereby we have a square root. Then from there, that will be the end of finding the domain of a function. So let's take example 4. Let's take example 4. So let's say the example said find the domain of function. Let's use f. We did this before, but let's use f. So the function name can be any letter. Normally you see f, but it can be G, A, K, L, M, N. It depends, Normally most textbooks use f, but it can be G, it can be H. So if you see it, don't be confused. So let's say that f, the function f of t. Remember that we always use x, but in this one we are using t. So it will be equals to t minus 2. Remember that we have talked about why finding domain means, excluding. So we will have a number line here whereby t is the independent variable. We have 0, then this one minus infinity, then we have positive infinity here. So we want to find So when you have a function, in fact, let's go back, that is having a square root. So all what you need to do, you take the expression within the square root. So what do you do with it? You write it again and then say that equals, it should be equals to or greater than 0. So this is the condition that we must attach to this. Why are we doing it? We want to make sure that this expression, if you substitute it t with any real number, should be, at the end of the day, should be 0 or greater than 0. So at the end of the day, we solve this inequality. So at the end of the day, this is a variable, this is a constant, this is a constant. So we move this to here. Obviously, it will be t greater than or equals to 0 plus 2. So t is greater than or equals to what? 2. So what is this is telling us? That the domain of this function f should start from what? 2, and it goes. So any number that is less than 2, like up to this part, should be excluded. Any number that is less than 2 should be excluded. That is, this part of the number line should be excluded from the domain of this function ft. If you put, for example, 1 is here. If we put 1 in this function, it will lead to taking a square root of a negative number. For example, let's even look at it. If we set t is equal, because this is the condition, that t that you should use here should be what? Greater than or equals to 2, meaning that it starts from 2, then it goes up to infinity. It is only true that then you'll have a positive number within here. Let's just take 1 and see what will happen and substitute. So we say that wherever we see t, we put 1 there. T is here, we put there. Then this 1 minus 2. So at the end of the day, we will have 1 equals to f of 1 equals to this 1 minus 2. This will give us 1. If you take your calculator, you want to solve this, you will have a math error. So the only way to avoid having negative here is to start t with 2. For example, if we say t, f of 2, that is t equals to 2, we will have what? 2 minus 2. So at the end of the day, we will take a square root of 0, which will give us 0. If we take 3 also, still we will have a positive. We'll have a positive. So this will be 3 minus 2 equals to square root of 1. But if the number, any number that is less than 2, it will lead to what? Having a negative number here. So that's why we have to exclude all the numbers that are less than 2. So to write the domain of this function, that is function f, it will be all, we can write it like this, is all the sets such that x takes all the real numbers, x take all the real numbers such that, but those real numbers, they should start from what? 2. So if you look at by number line, we have 0 here. So it is saying that the domain of this function f should start from 2, then it goes up to positive infinity. So this is where the function is defined. But any number that is less than 2 will lead to what? Taking a square root of a negative number. So this will be our domain of a function. And what it means, sorry, this should be t, rather, t, by the way. It should be t, not x. So we become so used to x that, so sometimes here it can be x, it can be t, it can be any letter. So it is telling you that the domain of this function is all the real numbers. But these real numbers, they should start from t. They should start from 2 and going towards positive infinity. So any number that is less than 2 it will make the function undefined. That is, it will make you to take a square root of a negative number, and which is allowed. If you take 1, any number, or even 0.5, it will lead to a negative number. And that negative number, you're going to take a square root of a negative number. So this brings us to different scenarios where you can find the domain of a function, but the takeaway from finding the domain of a function is this. If it is a square root or it is a fraction, then you have to exclude 1 or 2 numbers. If it's a fraction, there must be a number that you must exclude from the domain. If it is a square root, then there must be some restriction. So the restriction is this, that t, that is the independent variable, should be greater than or equals to 2. So normally finding domain of a function, it's complex when you have a fraction or when you have a square root. But other than that, then the domain normally will be what? Real numbers. However, in some economic applications, the domain would be what? Only positive real numbers. For example, let's look at this. This is economic application. We have this. Normally, we have price and quantity. So the domain here can only be what? Positive. Quantity is always positive. So we have to forget about this other quadrant. So this quadrant, when it comes to application, we have to forget about the negative quadrant. So all what we focus on is P and Q. So in most economic application, the domain of most of the functions should be positive real numbers. Price can only be positive. So if you look at a number line like this, for most of the economic application or business application, we only focus on this area. So we have P and we have Q. So most of the domain in economic application, the domains in economics or businesses or other social sciences, that the domain of a function is normally positive real numbers. But a question will tell you this. But when it comes to mathematics, there is no much restriction. So in application, there are sometimes restrictions whereby the domain can only be positive real numbers. For example, if you look at the relationship between price and quantity, price can only be positive. Quantity can also only be positive. So, if you find in the domain of that function, like demand function, the domain normally is positive. But the question will make this clear to you, whether there is a restriction or not. But here, so far, the takeaway is this. Finding the domain of a fraction, you have to exclude some numbers from the real numbers. Finding the domain of a square root, it has to be restricted. It has to start, the input has to start. The independent variable, which can be t in this case, or x in some cases, it has to be restricted. That is, it must start from some point. For this example, it starts from 2, going like this. So if you don't have a question, then we can go and look piecewise defined functions. If there is a question, please, you can go on and ask. Okay, so we don't have a question. So, so now we look at one of the objectives of this chapter is to understand what we mean by piecewise defined function. So let's, all what we are doing is a preparation towards understanding, doing differentiation. Some people will call it calculus, but we don't want to go there. Then we have problems with basic mathematics. So let's build the foundation, then, so that when we get there, we can go with a high speed. So piecewise defined function. Normally, we will have a function, but the behavior of this function is defined in parts. For example, we can have a piecewise function like this. Normally, it has two formulas. For example, you will have, of course, a typical of this. So we can have one formula where it says 1 over x minus 1. And it can also say another formula is 3x raised to the power of 2 plus 1. So, but we have two functions here. So first is what? F of x equals to 1. This said you use this if x is less than 1. So, but you use this one, the second formula, which is 3x raised to the power of 2 plus 1. You use this if x is greater than or equals to 1. So we have one function here, but with what? Two formulas. And what I mean by this is this is formula 1, formula 2. So the first formula said is x 1 over x minus 1, and the second one said f of x is equals to 3x raised to the power of 2 plus 1. So we have a function with two formulas. So if we have a function with two formulas, we call them piecewise defined function. So now let's look at this. We can go on and calculate this, but the key here is to build your intuition mathematically, what this function is trying to say. Now we have a number line here, and then we have 0. Then we have 1. We have 1. This is 1. Then yeah, we have, let's say we have minus 1 here. So if this one said x is less than 1, and when x is less than 1, obviously it's in this domain. Obviously, we have negative infinity, that's the last number, and here we have positive infinity. So the number line itself is what? X number line. So it is saying that when x is less than 1, we have to use the first formula. So in this range of the number line, that is from here up to here, we have to use 1 over x minus 1. But it is telling us that if x is equals to, that is from 1 here exactly, up to positive infinity, if the x value is that, then we have to use the second formula, which is f of x equals to 3x raised to the power of 2 plus 1. Sometimes we use piecewise defined function to avoid division by 0. You will realize that if x equals to 1 in the first part, if x equals to 1 here, like here, x equals to 1 here, it will lead to division by 0. So, and it will be what? Undefined. To avoid that, that's why they just stop the behavior of the function before it reaches at 1 for this one. So it's one of the reasons. One of the reasons we have piecewise function is to make sure that this function is defined. And what do we mean by defined? If we don't do division, but because if x is equals to 1 here, then it will be 1 minus 1, and that will give us what? 0. and it will 1 divided by 0, the function then will become undefined. So in order to avoid that, what do? Then we can divide the function into two formulas. The first formula, it will run from minus infinity before it reach at 1. Before it reach at 1. Because when it reach at 1, this formula, the first formula, it will lead to a division by 0 and the function will be undefined rather, it will be undefined. So the goal here is to make sure that the function is defined. So that's why we have a second formula whereby we only use the second formula if x is equals to 1 or greater than 1. So normally piecewise defined function is a way of making the function defined, because the first formula at 1, it will be undefined. So because of that, then we said that let's define it, let's have another second formula, whereby if x equals to 1, it will be defined. So it's just a way of making sure that the function is defined. So here, so let's say that we have a question that said evaluate or find and simplify that if x, so the f is minus 1/2. And another one said evaluate whereby f equals to 2. So we know that this x, it is just saying that x equals to minus 1/2. And we know that this is what? This is less than 1, but this one is what? Greater than 1. So the formula that we will use here, it will be f of minus 1/2. And since this minus 1/2, it's less than 1, we have to use this formula, that is 1/x. And x is what? Minus 1/2 minus 1. In second part, they said f of 2, and we know that this 2 is greater than 1. And if it's greater than 1, this is the part, because 2 will be around here. So this is the formula that we will use. In another word, if x is equals to 2, then this is the part of the piecewise defined function that we should use. So it will be what? F of 2 equals to 3 times x. And we know that our x is what? 2 raised to the power of 2, then plus 1. We have this. So at the end of the day, we go on. So this will be f minus 1/2 equals to, if you evaluate this, then you will have minus 2/3. If you evaluate this f of 2, then it will be, so this is 2 raised to the power of 2 is 4. 4 times 3 is 12. 12 plus 1, then you have 13. So normally this piecewise defined function, it just helps you to avoid a function becoming undefined. So if we have just stopped at here, if we have just stopped at here, then x equals to 1, we should be excluded from the domain of the function. So if we look at this one, the domain of the function, this first one, will be what? It will be set of all real numbers except what? Except 1. But if we look at this one, the domain obviously will be all real numbers, because there is no real number that will lead to division by 0 or taking a square root of a negative number. So if you look at this kind of a function, it would have 2 domains, one for this one, another one for this one as well. So for the first one, this is the domain, and the second one, this is the domain. So this is all what you need to know, the piecewise defined function. You should be able to know what they will give you. They will give you the function like this. and they ask you to calculate this. So you should be able to know whether you should use this one or this one. And also you should be able to find their domains for each of the formulas. This is the first formula and this is the second formula. So it's all what you need to know piecewise defined function. Basically, you have one function having two formulas. And why do we have two formulas? Is to make sure that the function is defined. It's just trying to skip, in fact, it's just trying to skip this one. So let's go on and look at the third fourth learning objective, which is the fourth is what we are going to look at some of the functions that we have in economics. Then so let's look at the functions in economics. Functions used in economics. So now we have some functions that they occur a lot when it comes to economics, business problems, or other social sciences problem. So we will look at these functions. We will look at them, and first we have seen the first one, which is, let's say, A, that is demand function. So we will look at this function, look at some of their characteristics, then we take real life applications or some problems in them. So when we talked about demand function, normally it's represented with dx. The d there is the demand, the x there is what? The quantity demanded. So equivalently also it can be represented as this, p equals to dx. So let's try to visualize this, this function. So if we try to visualize this like this, we have this, whereby on the vertical axis we have what? P, which is the price. And on the horizontal axis we have the X. So sometimes you will see Q is the same thing as quantity. So sometimes here will be, they will remove X and put Q there. It's the same thing. So now we have this. So demand function, what does it show? It shows what? Relationship between price and what? Price and quantity demanded. So it shows price and quantity demanded. So some people use it X or Q for quantity demanded. So if you can see that it shows the relationship between price and the quantity demanded. So the question is, what kind of relationship between price and quantity demanded? What kind of relationship do we have? Obviously, if you have taken principles of economics, you should be able to know this, because one of the prerequisites of this course is that you should take principles of economics. But right now, let's assume that we haven't. We started from the basic, that the relationship between price and the quantity demanded is always negative. And when two variables, they have a negative relationship, or sometimes we call it inverse relationship, graphically or geometrically, the slope between them will be downward sloping. So we have demand curve. So this is what our demand curve, or you can replace this with Q. So the relationship between them is, once you see this, you should know that the relationship between price and the quantity demanded is negative. So these are important. These principles of the laws of demand and supply is important. We know it. Sometimes it's not all about calculation. You can calculate, then I will further ask you to make some economic interpretations. So it's important we know these relationships, these concepts. So here, normally we should be able to calculate this. We should be able to calculate this. But we will take some example whereby we will find this. We can call this in mathematics. Normally P, is we normally math, we have Y here and here X. So normally we call this Y intercept. Or now Y, we can call it Y or P intercept. We should be able to calculate this. What does it mean? It means that if quantity demanded is 0, what will be the price? If this quantity demanded is 0, what will be the price? So here, normally we call it X intercept. So X intercept, or for this case, we can say Q intercept, that is quantity intercept. If price is 0 here, if price is 0, what will be the quantity demanded? But we will take a practical example whereby we will calculate these numbers. For here now, this is enough for you to understand that there is a demand function that we will be looking at, and it just shows the relationship between price and quantity demanded. So in another word, the relationship is negative. What it means is that if price increase in price will lead to what? Fall in quantity demanded, or we call X. X and quantity, they are the same. Or when there is a fall in price, it will lead to increase in quantity demanded, or increase in X. So if you looked at this very well, you will see that if price is going up, quantity demanded is going down. If price is going down, quantity demanded is going up. So it's because of this law. It's because of this law. That's why we said that the relationship between price and quantity demanded is what? Negative. Or they have inverse. It's inverse relationship. So from here, now we can look at another function, and that will be what? Supply function. So this will go off, but I will reconnect back, then we can continue. And I hope you also reconnect back. We can continue with the lectures. It's up to 11, 2 hours. So we also have supply function. So when we talked about supply function, we normally represent it as this. So whereby the X there is the quantity supplied. So you can replace X with Q. In some textbook, you will see it like that. So what supply function tell us? It just shows us the relationship. It just shows us the relationship some of you wait until an hour is gone, you logged in. You might have the attendance, but you might miss some of the lectures. So starting on time, I think, is key for you to understand. And on average, most of the students come after 30 minutes, an hour. But I think you are losing a lot. All right. So let's go on. So we have price here. We have X here. But this X is nothing but what? Quantity supply. So if you looked at supply function, what it is showing you is a relationship between price and quantity supply. So the next question is, what is the relationship? Is it a positive relationship or negative relationship? If you have taken a course a principle of economics, you will know that the relationship between price and quantity supplied is positive. What does that mean? If price increases,